Hi, my name is Samuel. Welcome to this lecture of chemical reactors in process systems. It will be three lectures. Today we will talk about the types of uh, chemical reactors and talk about the mole balance equations, design equation, and so on. And as you can see, you can find all of this, the material for these lectures on the book by Vogler, Elements of Chemical Reaction Engineering. The first lecture will be mainly on chapter 1 and chapter 2. So we will go chapter 1 to 1.5, and but anyway, this is just for your reference, so you can you know where to read in the book. But I think once you're there, you might want to also read a bit further than this specific sections. Then we will talk about rate laws. Rate laws are basically chemical kinetic laws that relate the rate of reaction to the concentration changes inside a reactor or in reactions. And then we will talk about stoichiometries, which will help us basically define rate laws in terms of conversion as a function of conversions. Then we will talk about isothermal reactor design, which is basically the simplest form of reactors. So here we will have basically a lot of assumptions just to simplify things. And then after me, Vincenzo will be teaching you on non-isothermal reactor design, basically where we will have change in temperature inside the reactor, which also causes other changes, and therefore the energy balance starts to become a bit more complicated. Yeah, so as I mentioned, this is the book, Elements of Chemical Reaction Engineering by Scott Vogler, and you can find it's very nice if you buy the book, but even if you don't buy it, you can find a lot of web resources and this link where you have all the chapters. For example, if we go to chapter 1, we can see that we have all sorts of examples and web resources. And you can even go to some interactive stuff. You have all simulation software guidelines for chemical reactor design specifically. You can see here, you have guides here and some examples also using those specific softwares that you can play around. I haven't really included much of the simulation tools or even simulation methods in my lectures, also because I think MES has taught you quite a bit on the modeling of process systems, and the chemical reactors are just one of those processes, and you will use all the differential equations that you learned there, and all the methods that you already have learned from the modeling of systems from MES's lectures. But if you want, you have a lot of examples here for MATLAB and Python, especially, which might be more relevant to you from this web source. Another thing is that, yeah, you have all these living examples as we are already on there, and then screencast lectures. So basically, you can also go here, and you have YouTube or other video sources to learn how to use for each of these sections. So you might also want to look into that. So that's I think nice, and I recommend that you really dive into this to just because not only for the exam, I don't think we will use much of this. I think the slides that I will be giving you and the lectures should be enough for what concerns the lecture, the exam, because the exam will also be based on a mini project. So I think, and the mini project will be based on what you learn. So I think that might be enough. But in general, since chemical reactors are very important in your professional career, and you will find them in all sorts of design problems. You might want to dive in further than what you learn in the lectures, to just have a better hang of it, right? Yeah. So yeah, that's my recommendation. Let's get back to the slides. We have I have structured the lecture like this. It will include the scope. Obviously, we will we will begin by stating what are the goals of this lecture and what will be your outcome. So what are your learning goals, basically, and then we'll start with basic definitions that we might need for exploring the rest of the course, and then we will talk about mole balances, because that's basically what chemical reactions are about, and then how these different mole balances actually behave inside the different types of reactors, the industrial types of reactors. We'll talk about very ideal types of reactors, which in real life will support you to design other real life reactors. So these are reactors with plenty of assumptions, obviously. Then there's a class assignment, but we might want to wait for that until the end of the lecture. Then we will talk about conversion in reactor sizing, and we will have some tools there to design the volume of reactors, or the time that we need for a chemical reaction, or for a reactor to take care of the chemical processes inside. And then we'll have a couple of assignments and some basic mole balance and conversion theories, and then reactor sizing with some tools. Let's begin with basically defining what chemical reaction engineering is. Chemical reaction engineering is basically it combines the study of chemical kinetics, so basically the chemistry of chemical reactions, and the reaction vessels, or the space where these reactions occur. We have, as you can see, the main pillars of chemical reaction engineering being the mole balance, because in every chemical reactor design, the most important thing is the mole balances. So basically the reactants, so how much of them do we have, and how do we want to proceed. And then we will have the rate law, so the rate at which they happen, and the stoichiometry, which is basically the relationships of the reaction with the concentrations, and then the energy balances and diffusion, contacting, and so basically, but the main mole balance will include rate law and stoichiometry, but mole balance and energy balance are basically the main pillars, I would say. And then we have different types of reactors and different analysis and assumptions that we can do here. We can have isothermal, non-isothermal, multiple single reactor steps, and so on. But we will get into that, I think, slowly. The scope, we can easily define it basically by saying that what you want to do with reactors is have design a reaction container, or a vessel, or a reactor that basically moves your reactions at the highest efficiency towards the desired output. And you would want to do that at the highest yield of product, so in a most cost-effective way. So the whole idea behind this is basically getting cheaper reactants and producing more expensive or more valuable products. From an example could be, for example, this the PTX plants that are now a hot topic. You get carbon dioxide. Well, that's not very cheap, but obviously, it depends. If you get it from the atmosphere, atmospheric carbon capture is quite expensive, but if you get it from a biogas plant or a cement factory where they have a lot of CO2 emissions, then that becomes quite cheap. So if you can upgrade this CO2 into a more valuable liquid fuel, for example, like methanol or other plastic materials and so on, starting from hydrogen and carbon dioxide, you're doing you're upgrading quite a bit, and then that final product becomes more expensive. So that justifies the design of the reacting system. But that's not only where we find chemical reactors. Chemical reactors are also just in our everyday life, things that we don't even pay attention to. Well, I need to. The digestion system has its own. It's a natural reaction reactor. Just the air above us is also a reactor because it has a lot of chemical substances that keep reacting and so on. So basically, that's what the scope is, and what you will learn from these lectures is that you will learn to define the rate of reaction. Then we will derive some of these general mole balance equations that are valid for any type of reactor, and then we will apply them to each and every of the main 4 industrial reactors, and then we will learn to size these reactors based on these equations. Some of the basic definitions that we will use today are a chemical identity, which is basically the number and the kind, the type, and the configurations of atoms within a chemical substance, right? And a chemical reaction is basically the change in the identity of these atoms within a molecule. And chemical reactions could be combinations, decompositions, or isomerizations. And give here some examples. Combination is basically when you put one molecule in the other and they produce a product, straightforward. And it can be reversible or irreversible, but then if it's reversible, it will be the backward reaction would be a decomposition, right? And decomposition is basically when you have a molecule giving rise to the individual constituents of the molecule. So basically it splits into its main components. And we have here an example where a cumene basically breaks into a benzene and propylene. And then isomerization is basically just rearrangement of the bonds within a molecule. So it has the exact same number of atoms and kind of atoms, but because the configuration of the atoms change, it just becomes different material. And this is called isomerization. So already the kind of bond in the configuration of the atoms changes the characteristics. And reaction rate is basically the rate at which this change in chemical identity takes place. So the loss in this identity happens at a pace based on the temperature, the concentration, and so on of our reactants, and the pressure, and so on. So those are our main definitions for this lecture. Now let's define mole balance, and to do that, we first need to define reaction rate a bit better. So if we have a reaction where A goes to B, as you can see, A is disappearing, so the reactant is becoming product. So if this should fully react, at the end of this, we will not have A, but we will have B. And B is forming. So, and the rate of reaction, which is basically the rate of reaction of A is the rate of disappearance, and the rate of reaction of B is the rate of formation or generation. And if we take, we will use this subscripts basically to describe the rates of reactants, but when we have a generic species, we'll just use J, and let's say we have J, and in that case, the rate of reaction of J is the rate of formation of species J per unit volume per unit mass. So that's the unit of reaction rate. It is basically mole of a species per unit volume per unit time. So and in some cases when we have a catalyst, when the reaction happens on the surface of catalyst and not on the volume itself, then we use mole per unit weight of catalyst per second, and that's basically how we describe that. Yeah, that's our rate of reaction, and it is a function of the properties of reacting materials and reaction conditions. And this is very interesting and important, because that's basically what allows us to make a generic mole balance that we can then apply into any reactor type. It does not depend on the reactor type. It just depends on the concentrations, temperature, pressure, and so on. So what if we find a rate of reaction for something, that will be applicable anywhere. So we can place the reaction into any reactor, and it will give us the same rate. So rate becomes a property and just a function of the property of the reacting materials. Yeah. And another thing which can be mentioned is that historically rate of reaction was defined as a change in time of the concentration, but it's not always like that, and we will look at that. So since it depends on the other parameters as well, it's a function of concentration, but it's not the gradient of concentration. Okay, it's not the change of concentration in time. It can be sometimes, but it's only for a specific case. So, for example, if we have a system here, it's this J is we have a system of volume. This is just a box, but it's very you can just assume like the system that Miss showed you, where you have a flow of materials and then exit of materials from it. And we can see that in if we have a molar flow of reactants into the system, the reaction will happen. So we will have a generation, which will be basically the multiplication of the rate of reaction of that species times the volume of that system. And if the properties are the same within the system, if we don't have change in density, then we can just integrate over the system and say that our G is basically the integral of rate of reactions throughout the volume. But generally, though, when we have reactions, we can also have accumulation. So basically, this generated species can basically stay within the reactor. So the generic form of the mole balance is we have moles flowing into it, then we have moles going out of it, we have moles generated because of the reaction, and moles accumulated in time in the reactor. And this is generic. We don't always have accumulation, and we don't always have the flows in and out either. So, but that's something that helps us define the mole balance for each reactor based on the assumptions that we make for that reactor. But for now, generally, this is our generic mole balance equation. Mole flow into the reactor minus mole flow out of the reactor that generated the species, and then and then basically the accumulation of that species within the reactor. And in this case, we usually just pick a species and track that. If moles of it are entered into the reactor, and then how much of it is going to go out, and how much of it is going to be accumulated and generated because of the reaction. Okay, so this is basically our basic equation of chemical reaction engineering. And then we can talk about the different types of reactors to which this is universally applicable. But then each one has its own peculiarities, which basically make it that we can simplify that generic equation to fit each and every one of them. So basically, this is chemical reactors, generic. This is our reactant system. And we have two types. We have the batch reactors and the continuous. Well, we have four types, but generally based on the steady state, on the state of the space. We can call them space-time, basically domain. We can divide them into batch and continuous reactors. The batch reactors, they are unsteady. They're in unsteady state, which means things change in time. Whereas the continuous reactors, they are steady state. So we have reactions that so basically that things don't change in time, they change in space in this case. In some cases, in other cases, they don't change in space either. And this can be divided into two: continuously stirred tank reactors and then tubular reactors. So the continuously stirred, they are, I think we will go to them through each in one of them later on. So this is just the general subdivision of reactors that you need for now. But now let's go to each and every one of them. We have the batch reactor. In a batch reactor, we basically put all the reactors together in the beginning, and then we proceed. We just dump them and then wait for the products to form. So basically our main parameter here is time, and this is just a scale up of what you would know a test tube or a beaker in a laboratory. You just put the reactors, you either stir it or just wait for it to react, and then we have our products. These can be quite slow because you're not really aiding them at all. You're just waiting for time. So they are particularly useful when you're doing experiments with new types of reactions, or when you need a cleanup of products, because then you can just clean up and they're suitable for small scale lab type. And if you want actually also more selectivity, because then you can wait long and then your products become purer, and then and you can basically see the product's progression with time. And examples of this are production of inks, dyes, polymers, and so on. So this more expensive stuff. To just illustrate how things look like, I can show you here. If we click here, we have this. We have basically this is what so we put the reactants, and you can see the color changing, and then they are removed. So and our process basically is in between the two, the in and out. So we only consider what's happening during the reacting process. There is the filling process, we ignore that. There is the extraction of the products, we ignore that. So basically our interest is just during this reacting process, and you can see the colors change because with time the reactants are becoming products. That's our batch reactors. So based on these characteristics, how can we apply the mole balance to this specific reactor? You can see that we said it's unsteady, which means it's transient. So we will have some accumulation because things will change in time, and the accumulation is the only factor that depends on time, so that will change. And then we make another assumption that it is perfectly mixed. So at any given time, the concentration and temperature of the whole vessel is the same, so things aren't changing they're changing in time, but they are not changing in space. So it's perfectly mixed, meaning that the concentrations at the top of the reactor and the bottom of the reactor are the same if you take them at the same time. But what we don't have, or at least what we don't consider in this case, is though the process of filling it up and removing the reactors, the products from the reactor. So in this case, our generic mole balance equation, we can just simplify it to basically remove the molar flow into the reactor and molar flow out of the reactor, and we just consider the main part, which is basically what happens inside the reactor, basically the generation part and the accumulation part. So the rate of reaction times the volume times the is equal to basically the accumulation. So those are the two things that are happening in such a reactor. Therefore, and if it's well mixed and we know it's we don't have variation within the volume of the reactor, so we can just assume that the accumulation is equal to the rate of reaction of that species times the whole volume of the reactor. And this is the mole balance for a batch reactor. And as you can see, what's happening is basically as A goes to B, we have a lot of A goes. We have a bunch of A's and no B in the beginning. We have the A axis on the left and the B axis on the right. And with time, we basically A becomes B, and then B becomes A, and then we have basically a bunch of B and no A, and then if we wait long enough, we will have no A, and we will have all the vessel filled with B. But if we, for example, pick a time one, a random point, then there we will have a if we use that design, that the mole balance, then we will have basically we can reintegrate this, and then we have T is equal to going from the point where we're pricking our time from the beginning to that time. We will be this will be the time that it takes to get us to this conversion, and that's a time, but it's also a conversion rate which will be associated to it, which we will see later. This is the time they're saying to basically move this amount of A to this amount. So basically we're still talking about the same species, but it will be much less here compared to here. So, and that is basically the time required. And basically the ratio between these two will just be our conversion rate. Now let's talk about continuously stirred tank reactors. Continuously stirred tank reactors are basically, they take from both worlds of the batch system and the flow system. They are perfectly mixed, so it's a vessel that's perfectly mixed, but we can continuously put in reactants and remove products. So they're continuously fed and they're continuously removed. So we can produce more things compared to what we would do with a batch, because in a batch, as you said, we wait. So the reactants are fed and withdrawn between while the reaction is still progressing. The costs are lower, as I said, so because we can continuously produce them. And they're preferred for larger scale liquid phase reactions where intense agitation is required. So they're continuously stirred, and that's basically what makes us believe, or at least helps us to assume, that it is also perfectly mixed, just like with the batch reactor. So at any given time, the concentration and temperature within this reactor will be the same, but unlike the batch reactor, any given time is also all the time, because we also don't have changes in time in this case, because it's a steady state reactor. And yeah, there's also possibility for auto refrigeration and more improved selectivity, especially when you put more of these reactors next to each other. Then you can improve the selectivity. For example, some reactor. Some products might need longer to react, so you can just put another reactor in, and you will have better conversion as you proceed. Okay, and just to see how this looks in, we have this animation here, and here you can see the color does not change. We're continuously putting in reactants and removing products, but we have the same level of reactants and the same level of the same concentration and temperature and everything within the vessel, so it remains the same, which means our reactants are becoming products the instant they get into the reactor. And that's what makes it profitable in a way, because as long as our conditions in the reactor are provided that those are exactly what we need, then as soon as we put our reactants, we can remove the products as well. And as mentioned, if we apply the general mode balance equation to this, we will get the assumptions are that it's a steady state, unlike the batch reactor, but it's perfectly mixed like the batch reactor. So in this case, we have in and outs because we are continuously putting and removing reactants in products, but we don't have accumulation. And at the same time, we can still assume that this is multiplied by the volume. So our mode balance in this case will be volume is equal to the difference between the flow in and out divided by the rate of disappearance of the reactant that we are dealing with. Yeah, and then we have the tubular reactor. In this case, it is a steady state. At any given time, the concentration will be the same throughout it will be the same throughout, so it means it will not change in time. But as we go from one point, from the reactant side of the tube towards the product side, we find different concentrations of the reactants and products. So which means the concentration will change in the direction of the axis, but it will not change in time, and it will also not change in the radial. So if we get a slice in that specific slice, it's as if it is a batch or a CSTR in a way. Yeah, mainly a CSTR. So some of the advantages of this are an even higher conversion rate per volume, especially compared to CSTR, for example. This is basically an improved CSTR because we're just putting the reactants and taking them as products every slice of the tube. And it's good for studying rapid reactions as well and large capacities. And this is usually used for gas phase reactions, especially with the aid of catalysts. So instead of just using the volume, you fill it up with catalysts, and then in that case we have something called plug flow reactors, which we will get there in a minute, which basically provides a nice space for the reactions to take place, and yeah, and then we have faster reactions that way in smaller volumes. And here is how it looks like. You can see that, yeah, we have, well, here they use a very similar color for the reactant products, but you can see that the color has changed because the concentration has changed towards the product side. And and you can see that this slice that you see here, it can be assumed that that is our reactants flowing towards the product side. And you can see here just the graph of concentration. The concentration of the reactants decrease and that of products increase along the axis of the tube. So that's basically what a tubular reactor looks like. That's the typical flow reactor that we have. And therefore, if we get back to the mole balance equation, we have still a steady state equation, so no accumulation. Steady state means no variation in time, so we have no accumulation here. And then we have uniform velocity along the diameter, as in tubular flow, and no radial variation in concentration. So along the radius, it's the same. And the velocity in the middle of the reactor is the same as well, and therefore we can just say in out in minus r plus generation is equal to accumulation. And basically in this case, we will just use the slice that you saw in the video for our purposes. And if you see that our in and out are not just into the reactor and out of the reactor, we can also assume that they are into one piece of the reactor and out of the second piece of the reactor, and we take just this piece of slice. Therefore, if we say we start from volume 2, from a volume V, then our slice will have a volume of delta V, and therefore in will be that, and out will be what's going out of the volume plus delta V. And our generation in this case will be the generation only in that volume. And if we just rearrange those, we will have basically the volume flow out of that piece of reactor minus the volume into the reactor is equal to, basically we just do minus here and the plus here, so that's what we're doing. So that's equal to the rate of reaction times the delta of the volume, or the volume of that piece of reactor. And if we divide by delta V, then we have basically an expression for the rate of reaction. And if you remember from your calculus courses, this is just the definition of a differential equation. Basically, this is definition of d of the flow divided by df dv, which is the rate of reaction. So we can in this case, usually in flow reactors, what we need is the volume that we need to design that's enough for the reaction to take place. So we can rearrange this to give as volume of the reactor, and the volume of the reactor in this case is equal to the integral of basically from the inlet to the outlet of the basically volume in flow, molar flow in to molar flow out is the derivative of F divided by R. Okay, so that's the volume necessary to reduce our initial molar flow into our molar flow at the exit. Okay. Pocket bed reactor is basically the same thing. Just as I said, it's mainly for gases, where we have a tubular reactor, but we fill it with catalysts. And in this case, the volume isn't really what we're after. We're after the catalyst weight, because it's the catalyst surface that gives us the reactions. Basically, reactants that do not touch the catalyst will not really react. So our aim is basically to find out how much of this catalyst will we need to get a specific conversion along that volume, or basically, so basically where however many catalysts you have, the more the better the reaction will proceed. And so basically in here we just substitute the volume of the reactor by the weight of the catalyst, and we have very similar weight of catalyst definition here. And that's basically the mass of the catalyst for a packet bed reactor. And these are typical in for example, reforming systems, which if we will be working in projects with the thermal systems here, either in the fuel cell section or thermal fluids, you might end up having to use a lot of these packet bed reactors, because those are most of the commercial systems that we work as well. And obviously real systems could be a combination of these different reactors, and so you might have to do some of the combinations of these notions to get your reactor design. So in summary, we can say that we have a batch reactor where we have no special variations, the same with the CSTR, no special variations, but in batch we have things that are unsteady, so things change in with time, and our design parameter is usually the time that it takes for a reaction to happen. In a CSTR, instead, we have a volume and we can find the volume by subtracting the flow into by subtracting the flow out of the reactor from the flow into the reactor and dividing by the rate of reaction, provided that we know our rate of reaction as a function of the conversion, which we will talk about in the second part of this lecture. For the other flow reactor steady state conditions are warranted because we have flows, so basically things can change along the reactor, but in time they will be the same. And you can see that our volume of reactor is an integral form, and is basically, yeah, as you can see, derivative of the flow, the molar flow, divided by the rate of reaction of A. And for a pocket bed reactor, we will have the same equation, but in this case, we substitute the volume of the reactor by the weight of the catalyst, which is basically the main ingredient that we need for reactions to happen in the case of pocket bed reactor. Okay, that's break time. Now that we have seen what mole balance equations look like for each of the different chemical reactors, by adding a conversion definition, which is basically how pure of products do we want, how much of the reactants do we want in the product. A definition of that basically will help us define the mole balances in terms of conversion, which will then give us design equations for the reactors. In these reactors, if we take a generic reaction that you can see here, AA, B go to CC and DD, which if we take this as a balanced chemical equation, then for all our calculations, we use the limiting reactant as the basis for proceeding. And the reason we do that is because a limiting reactant is basically the reactant among the two, or among the number of reactants that we have, that depletes the fastest, or that finishes first, which means it doesn't mean that it's going faster. It just means that we have less of it, and we cannot carry out further reaction unless we have enough of it in amounts, right? So basically, in this case, for example, we'll just consider A as our limiting reactant. We cannot know what's the limiting reactant unless we have what moles of a substance we're given, and what molar fractions of the reactants we have. Usually there is a mistake that it's easy to assume that the one that has less number of, for example, coefficient here, if this A was 1 and B was 2, people will just assume that since A has the molar coefficient 1, that will be the limiting, but that's not true, because how many moles we need is not what's defined in our limiting reactant. It's just how many of it we have in the available for the reaction. So anyway, that will become more clear, I think, as we work with examples later. But once we have that clarified, a conversion of a species, in this case, for example, A, XA is defined by the moles of A reacted divided by the moles of A fed. Basically, it's the ratio between what we're putting into the reactor and how much of it is disappeared. So it will be basically the difference between moles of A fed and moles of A remain in the reactor divided by moles of A fed. So we can just rearrange that and say that moles of A reacted we're just rearranging this XA is equal to moles of A reactor divided by moles of A fed, and we can just crisscross and multiply this, and we have this expression. And moles of A fed in this case, if we take a generic batch, it's just NaO times XA. So we can rearrange again. The ones that are remain are Na. So the moles of A at any time are Na, and moles of A fed, which is basically moles of A fed minus the moles that are reacted, and the moles of A that are reacted we said are NaO times X, so we can just define the moles of A, the conversion XA as moles of A fed minus the moles of A that we can actually measure, because that's when we measure concentrations that are remain in the reactor, divided by the initial moles of A fed. And differentiating this with respect to time and combining it with the mole balance equation that we know, which is basically R V is equal to dNA divided dt. This is our mole balance. We can just substitute for Na, which is this. Basically, we can put this in here and rearrange, and we get this equation. So basically, NaO dx dt is equal to minus rate of A times the volume of the reactor. And therefore, the time required for the reaction to take place or to achieve this conversion, because in this case we're talking about conversion, is can be expressed by this equation that you see here. Yeah, so it's basically similar to what we have, but in this case we are using the conversion to define our reactor time in this case, but then size when we go to the flow reactors. In fact, when we go to the flow reactors, it's the exact same thing. In this case, the conversion is dependent on the volume and not on how long we have waited, because as we said, these are steady state reactors. And basically what we do is we just change the moles of a species into molar flow of that species into the reactor. And in this case, we can just say that the molar flow of A times the conversion, the molar flow into the reactor, is basically the moles per unit time is the molar flow, so moles per unit time, and then moles of A reacted by moles of A fed. We just how we previously defined conversion, and then basically we can just cancel out moles of A fed by moles of A fed, and therefore the molar flow of A times the conversion is moles of A reacted divided by time. So this is the molar rate at which A reacts. This is the reaction rate in a way as a function of the conversion. And since we don't have any accumulation in this case, moles of A entering minus moles of A reacting, which is the disappearance of the reactancy here, is equal to moles of A leaving. So we're just removing the leaving from here to here in the generic mole balance equation. And just putting what we have here the moles of A entering, the moles of A reacting are molar flow entering times the conversion, and then what's leaving is basically what's not reacted. So that's the flow of A from the reactor. Therefore, the moles of A remaining or leaving the reactor are f of A going into the reactor times 1 minus x. And this basically is our design equation. So it relates the molar flow of the species with the conversion in the reactor. And just as we did with the batch, if we combine this with the mole balance equation that we previously derived, then we have such a a design equation where we have the volume of the reactor is basically the rate at which A is reacting divided by the rate of reaction. So the molar flow of A entering times the conversion divided by the rate of reaction. So what we're doing is just that we had this small balance and we're just substituting FA. So here, we're just putting this in here. Okay, and this is basically the volume that's necessary for a CSTR to achieve a specific conversion. A specific conversion is basically, that's our design parameter that we already decide we want this conversion, and if we know that's the CSTR that we want to run this reaction in, then the volume of the CSTR that will give us the conversion that we decide is basically this volume here. Okay? And since this is a flow reactor, the plug flow and the packed bed reactors will also have very similar design equations in terms of conversion. Just in this case, we will use integral form because things change through the reactor. So we have an integral form of the volume of the reactor. And in the case of plug flow reactor, we know it's the weight of the catalyst that matters. So the weight of the catalyst that gives us a conversion from 0 to X throughout the length of the reactor is basically this. Yeah, so that's the integral of the derivative of the conversion. Okay. So basically, in summary, we have here, these are the design equations, which are basically the mole balance equations as a function of conversion. And they look very similar to what we saw before, but in this case, we have the conversion, X, that is usually our design parameter. We say we want to convert up to 90%, 80%, 99%, that's up to us. But we should know that the more we convert, the bigger the volume that we will need, because you can see that, here, because the rates will be smaller and smaller, and then so the volume will be much bigger. Yeah, so that's the summary of our design equations. Now we will try to use some tools to help us basically design flow reactor sizes in an easier way, instead of having to integrate and yeah. And the way we do that is basically, if you can see here, we have this flow of the molar flow divided by the rate of reaction as a function of conversion in all of them. And you can just assume that this is a linear equation where you have y is equal to ax, because these are usually, this is basically usually unknown, and this is our y. And that way we can just make a plot where we have the FAO are on the y-axis, and then our x on our conversion on the horizontal axis. So yeah, so basically we just make yeah, that's quite a straightforward. Yeah, and then we can, once we have these, and provided that we have plotted our points like this, and we have a table of these parameters, then we can use something called Levenspiel plot to design our reactor. And as mentioned already, as the rate of reaction goes to 0, which means as we proceed with the reaction and we have less and less concentrations of reactants, then the conversion will proceed towards 1. But this can take quite some time if it is a batch, but it can also take quite some volume if it's a CSTR or a plug flow reactor. So the volume of the reactor is inversely proportional to the reaction rate, and which means the smaller the rate, the more the conversion. So if we want to approach to 100% conversion, we need a reactor that is really big. So that's why usually we will be satisfied with 90% purity or 95% or whatever. So we will still leave some reactants in the product, or we will have some other separation methods to get rid of them. But we will not wait, or we will not have volumes that give us 100% conversions. As an example, let's assume that we have rate of reaction as a function of x is somehow in the lab. This is something that we have to measure, and yeah, let's assume that we have this table. And as we previously said, we know the axes are FAO divided by RA and X. So we can put this on our X-axis, and we can divide this, we can divide the molar flow by these values and produce our FAO divided by minus RA. And if we take, for example, we have a molar flow into the reactor of A 0.4 moles per second, then our FAO divided by R will be basically, we do 1 over R and then FAO divided by R, and you can see that it here in the bottom. And then we can plot it like this. What you can see is basically, if we go back to this table here, now if we want a volume of a CSTR, what we will do is we'll just multiply what we have, FAO divided by minus R by Rx. So basically, for the conversion that we want, for example, if we want a conversion 0.2, or let's get a bit higher, if we want a conversion 0.6, what we will do is we will just multiply 0.6 by 3.5, and that is our volume of the reactor. So we basically have designed a reactor that way. And you can see that for a CSTR, that's the volume of a reactor, 0.8 times 8, for example, for 80% conversion. But you can see that it becomes different when we talk about plug flow reactors, and that's because we still have the FRAO, but in this case we have an integral form. So, and when we integrate the integral of a curve is basically the area underneath it, and so the shaded part is basically what we're looking at in this case. And this actually clarifies why we get a smaller volumes for the same conversion for plug flow reactors compared to continuously stirred tank reactors. You can see that for the same conversion, which is 0.8, which we took from here, we get 6.4 cubic meters of volume of reactor for CSTR, but we only get 2 cubic meters of volume of a PFR. So if we want to run the reaction in a tube along its axis, we will get a much faster, or not necessarily faster, but we will get, we will take care of this reaction in a much smaller volume than we would in a CSTR. Yeah, and for a PFR, we can use different numerical models, obviously, because we are integrating. So, but that's basically, we have solvers and softwares to do that. We can just integrate the area under a curve, and that's up to you. But in this case, for example, some of the examples are the 5-point quadrature formula, where you can just integrate this way. Then another thing we can do is basically we can put more reactors together in series, for example. And if we do that, in the case of a CSTR, for example, we get a less volume. So we can save volume of reactor by putting more reactors in series, especially for CSTRs. So basically, if we don't want to do a plug flow reactor, if the reactions are not appropriate for that, or if we are still dealing with liquid reactions, so we want to stick to CSTR, we can still reduce the volume of our reactor by splitting into more steps. So basically by putting more reactors together in series. The conversion, the definition of conversion for more reactors is basically it's the moles of A that have reacted up to the point that we're dealing with compared to, or compared to what was fed in the first reactor. So we still use the first reactor as our denominator for the definition of conversion. So xi, which is on ith reactor, is moles of A reacted up to that point, up to point I, divided by the moles of A fed to the first reactor. Because in this case, the exit stream of one reactor is the feed stream for the upcoming reactor. But when we talk about conversion, what we have the conversion in the last reactor is in comparison or in relation to what we fed in the first reactor. Here is an example. For example, here, if we take our initial molar flow of A fed into our first reactor, then we add another reactor. Here, when we talk about the volume of the second reactor, we will still use the exit of this one, which will be the feed of this one, as our FAO, basically. So this FA1 is FAO of the second reactor. And then, but when we talk about the conversion, this conversion 0.8 is in reference to this initial flow. I think it will be a bit more clear if we go through it step by step. So if we want the volume of the first reactor, we don't need to do anything. We just use the basically the design equation that we already obtained previously for CSTR. So the volume is FAO divided by minus RA times X. So this is our, just our Leibniz plot area. So that's the area of the rectangle that we already found. But for the second reactor, though, we will have to do our initial flow into the reactor. So the second reactor is our FA1. Our exit, as you can see, is FA2. However, when we talk about the generation in this case, we will use a different rate of reaction that's related to this conversion, and it will be rate of reaction in the second reactor for the species A. Because we have a more reacted species here, the concentrations of these ones will not be the same as these ones, even though we said that they are perfectly mixed and we have the same conditions in this reactor, but that then doesn't count anymore because we have different flows into the reactors. So the volume of the second reactor will basically be something like this. FA1, which is what's going into the second reactor, FA2, what's going out of it, divided by rate of reaction of A in the second reactor. Then if we add the molar flow rate at the 2 points and define conversion, so this is basically conversion in both cases defined in terms of the initial moles of A fed, and we can define for each one of them like this. We just use the conversions that are separate, and therefore the volume of the second reactor will be, we just substitute for FA1, FA2, this and this, and by rearranging we find that FAO will be X2 minus X1 divided by, the volume of the second reactor will be FAO divided by RA2, which is the same as we had before, but times the difference between the conversions and not just one conversion. And the way we do that is basically we can go back to our table, and what we see is here. So the volume of the second reactor is basically only this volume here. And we can just go back and do the volume of the first reactor, which we already know. It will be, we have 0.4, so we just take that x and multiply it by the ratio between FAO and R here. But for the second one, though, we subtract 0.8 and 0.4 to get the difference between the conversions. And therefore, we have 3.2 cubic meters. And you can see that this becomes the total volume of the reactors when they are in series is V1 plus V2, which is 4. And if you remember, the total volume that gives us 0.8 conversion, had we done this in one reactor, was around 6 or more. So anyway, this is to say that by putting the reactors together, or by putting reactors in series, we have reduced the volume of the reactor. And you can see that here. Before, the total volume of the reactor was this whole area here, but now it is this area plus this area. And interestingly, we can basically put a lot of CSTRs in series. As you can see, if we, for example, take each red point as a separate CSTR, we would have this rectangle for the first reactor, this rectangle for the second reactor, then this rectangle for the third, and so on. So you can see that the volume would be, we would shave all the stuff that is above the curve. And that is basically gives also as an idea that you can basically model a PFR as a series of infinite or very large number of CSTRs. So that's basically what it is. As we also, when we were deriving the mole balance equation for PFR, we saw that we were taking slices of the PFR along the axis, just take small slices and putting them and doing basically a CSTR type of operation in each one of them. And that's basically what's happening here. If we went infinite, basically we would just remain under the curve, and the volume of all these CSTRs would approximate to the volume of a PFR. Yeah, and yeah, so basically we've been using all this CSTRs that have the tendency where you have the conversion or the rate decreasing with conversion, but it's not always the case. Sometimes the rate can increase with conversion if it's, I don't know, endothermic, exothermic instead of endothermic, or non-isothermal reactor with changing volumes and so on. So sometimes a CSTR could have smaller volume than a PFR, as you can see, for example, in this example. So this is just to show that for a CSTR, it's always the rectangle. So for example, here, the rectangle would be this and not this, for example. It just stays under the curve. Whereas had we taken a PFR for this part of the reactors, for example, if we have these different reactors in series, then the volume of the PFR would have been this whole thing. And just to show you how the Levin-Schwab plot is basically dealt with. These are 3 different reactors. We take this one as a PFR, the others as a CSTR, and we find this. But for example, in this case, it would have been better to just take a PFR because you're gaining more volume here, and so on. Yeah. So that was basically it.